Okay, today we are going to start with region-based segmentation, and in this topic we are going to study these two techniques: region growing and region splitting and merging. Okay, so till now we have seen a segmentation based on the discontinuity approach. So where we try to find out the edges, lines present in an image, and in the next topic we are going to study segmentation based on thresholding. Okay, but sometimes these edges and thresholds do not give good results for segmentation. Okay, so actually the choice between these approaches depends on problem. Okay, so the choice is very problem specific. All these techniques have their advantages and disadvantages, and according to the problem we have to choose one of the segmentation technique. So region based segmentation is based on the connectivity of similar pixels. Okay, so here we are utilizing the similarity present in a region. Okay, so this is a similarity based approach, and here so we will divide our image into multiple regions in a such a way that, so consider we have divided a region in 4 regions, so every region will be uniform. Okay, so all the pixel in that particular region will have same property. You can talk about the intensity levels or a texture or a color. Okay, so all the pixel lying in one region will be uniform, so each region must be uniform, and connectivity of the pixel within the region is defined. Okay, so we have seen different adjacency like 8 adjacency, 4 adjacency, d adjacency. Okay, so we have to define the connectivity, and we have two approaches here. So first one is region growing and region splitting. Now the working of these two approaches is totally opposite. So as name suggests, here we will be starting with the seed point. Okay, so we will consider some points as our seed points. Okay, and then we'll start growing the region. Okay, and region splitting means we'll start with entire image and we'll keep on splitting that image into multiple sub regions. Okay, so working of these two approaches is totally opposite. So let us see some fundamentals. So basic formulation. So our given image will be considered as a single region which is represented by R, and consider after segmentation we have divided that image into n subregions denoted by R1 to Rn, and we expect these subregions to satisfy some properties. So they should satisfy these 5 properties. So union of this Ri's should be equal to our given image. Okay, so what is the meaning of this? So if you take a union of all these regions, if you take the union of these sub-regions, you should get a given image, original image. What is the meaning of this? That so this property will ensure the completeness of your segmentation algorithm. Okay, so this will ensure that no pixel is left out. All the pixels are included in one of the region. Okay, so segmentation must be complete. Okay, so this property will ensure segmentation must be complete. Every pixel must be in one of the region. Second property says Ri is a connected region. Okay, so this should not happen. So if this is one region and this is second region, and this is R1 and this is also R1, this should not happen. So what is happening here? So consider one pixel in R1 in this region and this one. Now these two pixels are not connected. Okay, so we should get one connected component. Okay, so Ri, any region should be a connected region. So pixel in a region must be connected in some predefined sense. Okay, so all the pixel in one particular region must be connected. Third point says Ri intersection Rj must be phi. Okay, that means, and Ri and Rj are different. Okay, that means we are talking about two different regions. Okay, they should be disjoint. Okay, so two regions should not overlap. Okay, so that is the meaning of this. and so regions must be disjoint. Next one, for each region we will define one predicate represented by p of ri, and for all the pixel present in that region should satisfy that predicate. Okay, so you can define the predicate based on the intensity level or a color value. Okay, so consider, so if I consider this region of a image, and consider this is a background region, and it is a white background, so I can define a criteria that the pixel lying in this region should have intensity value between 250 to 255. Okay, so all the pixel in this region should have intensity value in that range. Okay, so that will be my predicate. Okay, criteria. Second, last point says, so this Ri and Rj in this predicate are the two adjacent regions. So consider, so this is my Ri and this is my Rj. Okay, they are adjacent. Now predicate on their union. Okay, so union of those region would be this bigger region. Okay, predicate on their union should be false. Okay, so if the predicate is true on this union, what is the meaning of that? Okay, so now we should not have got these two regions separately, right? Okay, so what this property is ensuring, this Ri and Rj will be two different regions. Okay, so what is the meaning of this? The regions Ri and Rj are different with respect to this predicate. So Ri will have its own predicate, Rj will have its own predicate. Okay, so these are the 5 properties that these regions obtained after segmentation should follow. Okay, so now let us start with the region growing algorithm. So here we group the pixels or sub regions. So either we group the pixel or already found out sub regions into the larger regions based on the, so here we group pixels or sub regions into larger regions based on the predefined criteria for the growth. Okay, so what is the general procedure? First we will find the seed points. Okay, we start with the set of seed points. Okay, so in an image, first we will find the seed points at different locations. Okay, and finding the method to find the seed point is will be also different for different problems. Okay, first we find the seed points, and then from each seed point grow the regions by appending neighboring pixel with similar property. Okay, you start growing the region around that pixel. Okay, and all the pixels in that region should satisfy that predicate. Okay, so now if you change the similarity criteria, connectivity type and strategy to visit a neighboring pixel, you will get the different algorithm and you will get different output. Okay, so this similarity criteria is nothing but our predicate. So if you change the predicate value or the connectivity type and the strategy of visiting the neighboring pixel, you will get different algorithms and different outputs. Okay, so now strategy to visit neighboring pixel means what? Either you are going in a BFS fashion or DFS fashion. Okay, connectivity type, we have 3 choice here: 4 connectivity, diagonal connectivity and 8 connectivity. Similarity criteria, you can increase the range or decrease the range. Okay, next thing we have to decide is stopping rule, when to stop. Okay, so generally we stop when no more pixel satisfy the criteria. Okay, so this is one example. Now this is the image of welding, image showing defective welds. Now this darker portion, okay, this darker region shows the welded part, and this is the surrounding surface of the material, and this bright part is showing the defect in the welding. Okay, so it is showing the cracks in the welding or porosity present in an welding, and this is actually a X-ray image. And why we are getting a brighter spots here? So if you are taking if you are passing X-rays from over that material, the attenuation of X-ray will be less in this cracky region. Okay, so those X-ray will go through those cracks. That's why we are getting a bright region here. Okay, and now we are interested in segmented we are interested in to segment these cracks. Okay, so what is our first step? To find the seed points. Okay, so we can just simply do the thresholding to obtain this result. Now how to decide the threshold value? So for that, okay, so first step is seed detection, all the pixels with intensity 255. As you can see in this image, the seed point can be this brightest pixels. Okay, and if you plot the histogram of this original image, as you can see, we have majority of the pixel with this intensity, and these are the surface pixels. Okay, and these values are representing our cracky region. Okay, so now in order to find this thresholded output, we have set the threshold as 254. Okay, that means these crack points, the crack pixels are having intensity 255. Okay, now seed points are means we have found out the seed points. Now next step is we have to grow region surrounding these seed points. Now what is our criteria? So our predicate is the absolute gray level difference between any pixel and the seed should be less than 65. Okay, so now the pixels surrounding those seed points should have intensity value between so it would be 255 minus 65 to 255. Okay, so what is the result of this? So it will be 190. So 190 to 255 intensity values will be considered. Okay, and we are considering 8 connectivity. Okay, so those pixels should be connected to this seed points, and their intensity value should be in the range 190 to 255. Okay, so we have successfully found out those region. Now what we are doing, we are finding the boundary of those regions and we are superimposing on the given image. Okay, we are superimposing those boundaries on the original image, and this is our output. Okay, now this application will be used on the inspection line in the industry. Okay, so the material will be passing through the X-ray detector, and the application will be running, and the application will find out these cracks. Okay, now what is the algorithm? So fxy will be our input image. Sxy is known as a seed array. Okay, so initially Sxy will have one value where we have a seed points and 0 otherwise. Okay, and Q is our predefined predicate criteria. Okay, so first step is to find the seed points. Okay, find all connected components in an Sxy and reduce each connected component to 1 pixel, and label all such pixels found as 1 and all other pixels in S as are labeled 0. Okay, so just find one pixel, okay, and you label that as 1, and other pixels are labeled 0, and the pixel with one value will be treated as seed points. Next we have to form this FQ image. Now FQ image contains 1 for the pixel XY if it satisfies that predicate Q. Okay, so form an image FQ such that at each point XY, FQ equals to 1 if the input image satisfies the given predicate Q at those coordinates, and FQ 0 otherwise. Okay, so FQ is formed, this image is formed. Now we have to grow the region. Okay, so step 3 and 4 are responsible for region growing. So what is this? So let G be an image formed after appending each seed point S all the one valued points in FQ that are 8 connected. Now what we are doing, we are appending each seed point in S and the one valued points in FQ. Okay, so one valued points in FQ already satisfied that condition, right? So we are appending seed points and those points. Okay, and here we have considered 8 connectivity. Label each connected components in G with different region labels. Okay, so the step 4 is responsible for labeling. Label each connected component in G with different region labels. Okay, integers or letters. This is the segmented image obtained after region growing. Okay, so this is the region growing algorithm. You first find out the seed point, then you find out the pixel satisfying the predicate. Okay, you connect the seed point and those pixels and label the regions. Now what are the advantage? Borders found are perfectly thin and connected, and it is very stable with respect to noise. Okay, so now noise will be taken care by the condition. Okay, now second technique is region splitting and merging. Now here we follow top down approach. Here we follow top down approach, and its working is opposite to the region growing. Okay, so first, what is the general procedure? So first we'll start with the largest region, possibly the entire region, entire image. Then the predicate is used to determine if the region is uniform. Okay, so we will define our predicate, and for the given image, the entire image, will see whether it is satisfying the predicate. Okay, so if it is a uniform image, okay, not containing anything, so it will satisfy, otherwise predicate will be false. And if not, split the regions into 4 regions. Okay, so we divide that image into 4 regions. Okay, so we have to decide the shape of the division. Okay, generally it would be rectangle. Then each of these 4 regions is independently tested by the predicate. Okay, we apply the same procedure on these sub regions. Okay, so we'll consider this region and we'll apply the predicate. If it is not, then we'll subdivide it and continue this procedure. Now this will be our splitting part. Okay, then we will get some. So consider after splitting, consider we have obtained these 2 adjacent sub regions, and it can happen that these 2 adjacent regions are uniform. Then we have to merge these neighboring regions. Okay, this procedure continues until all regions are uniform. Okay, so what is algorithm? Split the image into 4 disjoint quadrants, any region Ri. Split into 4 disjoint quadrants, any region Ri. So split the Ri in 4 disjoint quadrants for which the criteria is false. So Ri is not satisfying that criteria. So we are representing the criteria by Q here. Okay, so if criteria is false, you divide that. When no further splitting is possible, merge any adjacent regions Rj and Rk for which the criteria is true. If you take the union of those regions, okay, the union is satisfying that criteria, so you merge those adjacent regions. Okay, they should be adjacent. Okay, next, stop when no further merging is possible. Okay, so diagrammatically it will look like this. So we have, so this is our R region, R image. Okay, so the root, so this tree is known as a quad tree. So root of this quad tree would be our input image. Okay, and then we have divided that image into 4 sub-regions, and let us consider R1, R2 and R3 are satisfying the predicate, but R4 is not, so we have divided that into 4 sub-regions. Okay, so same is written here. So this is our splitting stage, and then we have to merge. Okay, so if the 2 adjacent regions are, union of those is satisfying, then you have to merge. Okay, and stop when no further merging or splitting is possible. So this is one example. So here, so this is the final result. As you can see, this stem of this leaf, can you see the stem? So stem is present here, but it is erroneously removed after, in the final output. This is second example. Okay, now this is the image of Cygnus loop. Okay, Cygnus loop, this is one supernova. Let me show you the color image of that. It is present on NASA website. Okay, so this is the image of supernova, and this is a cloud of super hot dust and air. Okay, and this is the X-ray image of that, and we are interested in finding this outer lessly dense region. Okay, so we want to find this region surrounding this highly dense region of cloud. Okay, and we have a constant background outside. Okay, so now what will be our criteria? As you can see, we have very randomness in this region. Okay, in the outer area. Okay, so what we can do, we find a standard deviation. Okay, and if the standard deviation is greater than some value, okay, we can consider that pixel. And in addition to that, now as you can see, the intensity value of this cloud is the highest, background is having very low value. Okay, so this MR is representing the mean of intensity value. Okay, so if mean of the intensities, if it is between the 0 and B, okay, then we can consider that pixel. Okay, so we are having two conditions here, and both should satisfy. Okay, so if the standard deviation of that region is greater than some value, and if its average is lying between these two value, then we can consider that pixel, otherwise false. Okay, so now, so these are the three outputs for different sizes of the quad tree. Okay, so if the final quad region, if you set to 32 by 32, this would be the output, then 16 by 16 and 8 by 8. Okay, so now for the 16 by 16 we are getting the best result, because here we are getting the discontinuity. Okay, so this is done. Okay, so in next class we will be seeing the segmentation based on the thresholding. And one more thing I want to share. So as you can see, so we have 20 marks for CA and 20 marks for MSc. Okay, so for the CA, we have conducted one MCQ test. Okay, for the, and I will consider 10 marks for that MCQ test. For the remaining 10 marks, you have to complete one assignment, and for that, what we are going to do, okay, so now you have to form a group of 7 students. Okay, so we have total 42 students in DIP. Okay, so we'll get a 6 groups, and then you have to create a GUI application in MATLAB. Okay, now here we'll have a frame for the input image and frame for the output image. You have to provide a browse button. Okay, through the browse we'll read the input image, and you have to provide at least 7 options. We have seen different methods in image processing, like to find the negative image. Okay, for contrast stretching. Okay, so first you can provide buttons for different methods, and if I click on that, okay, I should get the output image in the neighboring frame. Okay, for some tasks you have to provide a slider. Okay, like contrast stretching, you can provide a slider there. From the slider the threshold value will be obtained. Okay, so for each button you have to write a function. So every student will write a function for one button. Okay, so what we have to do, you have to form a group of 7 students, so we will get 6 groups. Okay, and we'll decide the deadline of this activity. Okay, and this activity will carry 10 marks. Okay, so I think problem statement is clear to you. I will provide one sample to you, okay, how to create that. Okay, and for the lab, so this is our lab. So we have 60 marks for the internals, and total we have 11 practicals, and if the weightage of one practical is 4, so we will have 44 marks, and then your record will carry 10 marks, and I will conduct viva for 6 marks. Okay, so that will be the split of this 60 marks. And so in this fourth unit, so we have discussed till now point, line and edge detection. Finding gradients using mask is also done. Okay, so we have seen 3 gradient operators, and then the region based segmentation is also over. So only one point is remaining in this unit, that is thresholding based image segmentation. Okay, so we will complete this topic in next lecture. Okay, so any doubt?